Hello. In today's lecture, I will be reviewing very fast what are the different forms of energy and when do we use conservation of mechanical energy, and then we will do 3 simple exercises to practice the concept. So the 3 forms of energy so far, we learned kinetic energy, gravitational potential energy, elastic potential energy. We have kinetic energy when an object is moving with a velocity v. We have gravitational potential energy when an object is at an altitude h above a reference surface. We have elastic potential energy when a spring is compressed or elongated at distance delta x. Mechanical energy is the sum of all these energies. If friction is neglected, that is, there is no friction, then we can use conservation of mechanical energy, which is mechanical energy initial equal mechanical energy final. Let's apply it. So we have this exercise 5, page 34 in your booklet. A diver of mass m drops from a board 10 meters above the water surface. Okay, so we know that he was here, 10 meters above the water surface. Okay, neglect air resistance. Use conservation of mechanical energy to find his speed at position 1. So as we learned today in the live session, I come here, I see he has an altitude h, implies he has GPE. Okay, does he have kinetic energy? No, because he just drops himself, and it says here kinetic energy is 0. So he only has GPE, so mechanical energy initial is only equal to GPE initial, which is mgh initial. Okay. Now we want to find the speed at position 1. So we come at position 1. What do we have at position 1? He has some altitude, let's call it h1. It is 5 meters, implies there is a GPE, let's call it 1. Okay. And he has some speed because he's still moving. So let's say it is V1, implies he has kinetic energy 1. So mechanical energy at position 1 is equal to GPE 1 plus kinetic energy 1. So let's apply the conservation of mechanical energy. So we say mechanical energy initial is equal to mechanical energy at position 1. Mechanical energy initial is GPE initial. This is equal to GPE 1 plus kinetic energy 1. GPE initial is mgh initial. This is equal to mgh 1 plus half mv, let's say 1 squared. And we are applying this because there is no friction, there is neglect resistance. Okay, so we are up. So here, because there is no friction or resistance, so we can apply conservation of mechanical energy. Now let's solve for V1. So I can divide by m. I divide by m the whole equation because I don't have it anyway, so I can divide by it. I divide by m, and I end up with g h initial equal gh1 plus half mv1 squared. So g is 10 times h initial was 10 equal G10 times at position 1 it's 5 plus half V1 squared. So I get 100 equal to 50 plus half V1 squared. This will give me half V1 square equal 100 minus 50, which is 50, which means V1 square will be 50 times 2, 100. V1 equal square root of 100. V1 equal 10 meter per second. This is part A. Oh. Part B, let's do it here. Use conservation of mechanical energy to find his speed at position 2. So I'm going to use the same thing, mechanical energy initial. This is equal mechanical energy at position 2. Now let's come at position 2 and see what do we have. At position 2, there is V. So there is V. They're calling it V final. Let's call it V2. Implies I have kinetic energy, which is half mv squared. Okay. And it is at the reference, so there is no height. Height is 0, so there is no GPE. So mechanical energy 2 is it just KE2. So I come here, mechanical energy 1, it's mgh1. This is equal half m v2 or v final square. Okay, same thing, I divide by m, so I get G, which is 10 times H1, 10 equal half M, we divided by it, V2 square. So I get V2 square is equal to 2 times 100. So this is equal to 200. V2 is equal to square root of 200. V2 is equal to 14.14 meter per second. Okay, you can find the full solution over here. Let's do another exercise. This one I solved today in the live session, so we will do it quickly. So the slider down in the figure shown in the figure below starts from the top on a frictionless surface. So I have a frictionless surface. Implies I can use mechanical conservation of mechanical energy. That is mechanical energy initial equal mechanical energy final. And slice down into the value. What initial speed V does the slider need to stop at the next hill? So here V final is equal to 0. So what forms of energy I have here? It is at an altitude h, implies there is a GPE equal mgh. There is V initial, implies there is KE equal half mv initial square. Okay, so mechanical energy initial is equal to mgh plus half mv initial square. At final position, there is height, altitude, there is h, implies there is a GPE final, if you like, GPE, which is mgh final or whatever. Okay, there is no V final, so there is no kinetic energy. So mechanical energy final is equal to mgh final. Now, in order to get the V, we will use mechanical energy is conserved. So mechanical energy initial is equal to mechanical energy final. Mechanical energy initial is mgh plus half mv initial square, right? This is equal to 5 point, this is equal mgh final. So we also divide by the m, and I get 10 times 4.2 plus half v initial square is equal to 10 times 5.9, which is the final height. So 42 equal 42 plus half. Here we did a mistake. What is it? 10 times 4.2. Okay. So 42 plus half the initial square is equal to 59. I solve it just as we did in the live session. You can go there to check exactly how the math goes, and we get the initial is equal 5.83 meter per second. So for full calculation, check live session 30, 11, 21. Okay. Okay, so let's do one last exercise, which is a bit more lengthy. So here, what I show you is that 1 is what happened here, then 2, what's happening here, then 3, when we put mechanical energy initial equal mechanical energy 1. The last problem we will do is exercise 1, page 30, page 41. So a ball of mass M equal 200 grams. So let's put the given. This is mass M, 200 grams implies mass equal 0.2 kilogram. Okay, it's pushed to the left against a spring of stiffness K1 equal 100 Newton per meter. So this is the given. Spring 1 is compressed by a distance x1, which is also what we call delta x1. So let's stick to delta x1. This is 0.15 and then released from rest. So at position x1 equal 0.15, V1 was 0. Okay, the spring pushes the ball back to the right, and when the ball passes by the equilibrium position, that is when it reaches here, when it reaches delta x equal to 0, okay, it moves, it has a speed v0. It has a speed v0. The ball then moves up a frictionless inclined plane, so there is no friction, implies we can apply conservation of mechanical energy. Of height h equal 0.2. So we have this height h, 0.2. Before it compresses another spring having the same stiffness K2 equal K1 equal K. So once the ball reaches here, it will reach the spring and it will compress it. Okay, it will make the spring get compressed. Okay, use energy conservation, calculate the speed V0 of the ball. Okay, so we have information about what is happening when it is compressed. So let's say this is 1 here, and then this is 2 here. So what's happening at position 1? What do we have? We have a compressed spring, implies there is EPE, which is half K delta X, they call it 1 square. Okay, it's at rest, so there is no kinetic energy. It's at the PE equal to 0, so there is no GPE. So mechanical energy 1 is equal to half K delta X1 square. Okay, I can do the calculation. I can get it. Mechanical energy 1 is equal to, it's equal to half K, which is 100 times delta X1, it's 0.15 square. Okay, the answer to this, half times 100 times 0.15 square, it's mechanical energy 1 is 1.125 joules. Okay, so this is mechanical energy 1. Now at position 2, what do we have? We have an object. We have V. We have V initial, implies there is kinetic energy, which is half mv1 square, right? So what is mechanical energy at position 2? Let's call it 2. This is equal, or actually they call it V0, so let's call it V0. So mechanical energy at position 2 is half mv0 square So this is equal to mechanical energy 1, or let's also calculate for half m. So half m is 0.1 V0 squared. Now I will do it over here. Mechanical energy at position 1 equal mechanical energy at position 2. So 1.125 is equal to, sorry, let's put it here. Mechanical energy at position 1 is equal to mechanical energy at position 2. So 1.125 is equal to 0.1 V initial square. We calculate this, we get V initial square is equal to 11.25. V initial is equal to 3.35 meter per second. Okay. Okay, part B. So we will continue here. Part B. Calculate the speed of the ball when it reaches point B. So now this is third position, at position B. Here. Let's call it position 3. We want to calculate the speed. Okay, so what's happening at position 3? What's happening? First, it's at an altitude, so there is a GPE, right? Because there is H, and kinetic energy because there is V. The question is actually to calculate this speed. So there is V, let's call it V at B. So now we will say mechanical energy initial or mechanical energy at position 1 is equal to mechanical energy at position 3. Mechanical energy at position 1, we calculated it, it's 1.125. This is equal mechanical energy at position 3, which is mgh plus half mvb square. And this also, let's say it's hb. Okay, so we solve 1.125 is equal m, which is 0.2, times g, which is 10, times hb, which is 0.2, plus half m, which is 0.2, times vb, I'm supposed to calculate it, square. Okay, so we will, so this will give me 1.125 minus 0.2 times 10 times 0.2, which is 0.4, is equal to half times 0.2, which is 0.1 VB square, right? So let's put this V capital V. Okay, 1.125 times 0.4 is 0.725 is equal to 0.1 VB squared. VB squared will be equal to 0.725 divided by 0.1. This is 7.25. This gives me VB equal to square root of 7.25, and that's 2.7 meter per second. Okay, this is part B. Part C, calculate the maximum compression X2 of the spring. That is, the ball will reach position B. It has a speed V. It will hit the spring and it will compress it by a distance XB. So here there will be a distance X maximum. Let's call it X maximum, which is the compression in the spring. Okay, so now we are at this position. when it is maximum compressed. This is position 4. Okay, so let's solve here. Okay, what at position 4, what is the form of energy we have? First, it's at an altitude h. So there is GPE, which is mgh of B, which is the same altitude. So this is 0.2 times 10 times 0.2, which is 0.4. Okay, so we have GPE. This is first. What else do we have at position 4? There is a spring which is compressed. So we have EPE, which is half K delta X, let's call it X maximum square. So this is equal half times K. K is 100, so this is 50 delta X maximum square. And the question is to calculate this X maximum. Okay, what else do we have? Do we have a kinetic energy? We don't have a kinetic energy because it says that it is maximum compression. So it will do the compression and it will stop. So there will be no kinetic energy. Okay, so now in order to solve this, we will say mechanical energy. So what is mechanical energy here? Mechanical energy at maximum compression or at position 4 is equal to 0.4 plus 0.4 plus 50 delta X maximum square, because it's the GPE plus EP. Okay, now to solve this, let's just make some space. Okay, so we will say mechanical energy initial, which is at position 1, is equal mechanical energy at position 4. Mechanical energy at position 1, we calculated it, it's 1.125. This is equal mechanical energy at position 4, which is 0.4 plus 50 delta X maximum square. Okay, so 1.125 minus 0.4, this is 0.725 is equal to 50 delta X maximum square. 0.725 divided by 50, it's 0.0145 equal delta X maximum square. So we get delta X maximum to be the square root of 0.0145, and that's 0.12 meters. Okay, so in this problem, we use conservation of mechanical energy to find different things at different positions. That's it for today's lecture. Tomorrow, we record a new lecture. Bye-bye.